Hi everyone, we are team NeuroBand. I am Girish with my teammates Karthik and Viren. Did you know that globally, falls causes around 7 lakh deaths every year, making them one of the leading cause of accidental injury related death? And in India, studies shows that one third of older adults experience a fall, often with serious consequences. That's why we build NeuroBand, not just a panic button, but a truly intelligent wearable. NeuroBand continuously monitors motion, heart rate, and ECG signals and uses smart logic to identify real emergencies while filtering out false alarms. When a dangerous situation is detected or the user requests help, NeuroBand enters help mode. It plays an audible SOS, alerts caregivers, and streams live data to our mobile app, where vitals, movement status, and ECG history are displayed in real time. We are thankful to DigiKey for supporting and making this project possible. Now stay tuned for the live demonstration.
Hi everyone, welcome to this demonstration of our project NeuroBand. My name is Karthik Khandelwal and I am the second member of this team. So in this demo, there will be a few scenarios in which I will show you the effectiveness of this fault detection system in our project. First of all, I am very grateful to Circuit Digest and DigiKey for selecting our project and sponsoring and giving us this board so that we can demonstrate our project. So in the first case, the elderly person is just standing and he falls down to the ground. Something like this. So as you can see, the beep goes on and the doctor is informed as well as the friends or relatives of the family in the app. So to stop this sound, either the doctor will come or the patient can just press on the OK button there. So with this, the beep is stopped and the doctor knows that you have stopped it. So this was the first scenario. In the second scenario, which is the most frequent one, in which the person is actually sitting doing something and he just falls. Something like this. So this was the second case. To stop that, press OK or select button. In the third case, the person is walking. He's coming and then he suddenly has a stroke and then falls down. Right. So now this was the first jump in which you can see the person is falling. But there is also another demo in which I will show you what will happen if the person's blood pressure gets too low or too high. So this is the second demo of our project NeuroBand. In this second demo, I will show you how our project deals when the blood pressure BPM rate goes below 40 or below or above 110. Right. So these are the thresholds that we have kept. Now you see these values we can't generate in real life right as of now. So for that I will make use of software from a Node-RED dashboard and I will simulate it and show it to you. Right. So right now the blood pressure is 70 and so nothing is happening. But when I do it to 35 around here and then wait for a few seconds. So like you see the blood pressure goes down here and then accordingly it will just start beeping. So which means help is needed. So it takes after few readings, which is our intelligent system and our software, right? So here like I press the select button to stop it. Next you can see, next I will show you what happens when it goes above, right? So if it goes above 110, so wait for a few seconds here and then as you can see the help started and the doctor has been warned that something is wrong here, so he will able to help the patient. So this is what happened here. Till now I have talked about like how I trained the neural network model to deploy on the device and
uh, used it to detect fall, walking, or sitting, or any kind of other movement. So to do this, I used Edge Impulse platform to train the model. So to start, you need to click on Get Started or Login. Since I already have account, I will press on Login. Right. So you need to create a new project, and I've already created a project NeuroBand. So I will press on here, and then you need to go to data acquisition. As to train a model, you need lot of data. So here you need to upload your train data. So for any sort of demo data, I will add the Kaggle dataset link in the description of the YouTube video, so you can look there. So after adding the data, you need to go to create impulse model, create impulse tab, and here you need to add the processing block and the learning block. For the processing block, you need to select spectrum analysis, that it is best for accelerometer data. Then for the classification block, you need to select classification, because any other type of blocks will be useless for us, as we want to do classification. Then press on save impulse, then go to spectral features, where you need to, which is basically just feature extraction of the data that we are giving to it. So you need to press on auto tune parameters, and it will auto tune all the parameters that are given, as well as after running it, it will also show you the on device performance of the uh, of this block. Next, you need to go to classifier. Here you need to set the number of training cycles, learning rate, and training processor, which will be always set to GPU. And the advanced training settings, if you want, you can do it. And just press on save and train. About the neural network, it will already was selected when you added the classification block in the create impulse tab. So just you need to just press and save and train. After training, it will give you the logs of the last training performance, like the accuracy and the loss. Now I can see that this is really great, and my model has trained really well on the dataset that I have given. So I can just skip to live classification and model testing. But if by chance the model is not trained perfectly, you can go to EN Tuner. EN Tuner is a proprietary software of the Edge Impulse, which is used to further tune the model. Just press on new run, select your objective. Here it will be minimize latency, and use a template. You can use any other template. This is basically just hit trial and run. You need to select one and then see the results yourself. Uh, if it comes up to par of your, like how you wanted it, then you can just add this block to the impulse design, and then retrain the model here. Next, you need to go to live classification. Now here you can classify an existing test sample, or you can classify new data while with, if you want to connect it to a phone or to a ESP32 device, and then press on start sampling. So since I already have a data, I will press on load sample, and it will take some time to do it. Now yeah, so here select the quantized unit version, and you can see how well your model has performed. Since it was a fall data, like so you can see it has perfectly detected it was fall. So my model is really performing well. And then you need to go to deployment. So after going to deployment, you can see a deployment target. You can make it C++ library, Arduino library, and any other sort of library. So to support ESP32, you can use a C++ library or Arduino library. I'm selecting Arduino library here. Select inference engine as EON compiler. Select it as int8, and then press on build. After building it, it will give you a zip file, which you need to extract it in your include folder, include library folder in your project. Now now comes the main part. How do I actually implement this code? So to do that, you need to go to the view docs here. Right, so since I've already opened it, so yeah, it's here already. So you can see how it's actually done. Here you can see like how I use the impulse classify function to get the sensor values, its total then, and get data, and how to fill the buffer, and how do I actually get the final output. It is all written here. You can even go to C++ library on custom boards and check how do I exactly do this, what is the meaning of each function. So yeah, so this is how I actually did it. You can also see in my VS Code library here. So my model was fault detection. It gives me source files. Now here's the impulse SDK model parameters, my TF flight model, and based on that I created my main.cpp file, which is this, like how I initialized my accelerometer and then how I got my data. It is all written here.
Hello everyone, my name is Viren Sharma and I'm the third member of NeuroBand team and I'll be explaining the software architecture of this project. I would like to thank Circuit Digest and DigiKey for giving us this opportunity of doing this project. So as you can see, I've first moved into the README file. I would highly recommend to the people who are trying to implement this project to go through the README file. So since I'll be explaining the software architecture, I'll first start with the FreeRTOS task breakdown. So there are different tasks that have been allocated to the different cores. The compute and the UI related tasks have been dedicated to the core one. So the HML inference model for fault detection, for the UI updates for OLED and button input management have been allocated to core one. And core 0 handles the ECG sampling, the I2C sensor polling, and network communication. So now I'll quickly move to the main.cpp. So as you can see in the main.cpp, we have defined all the parameters for PWM, the SOS timings, the threshold timings, and all the variables. And all the global variables have been defined at the top and all the tasks. So these are all the tasks that have been defined, the FreeRTOS tasks that will be used and that have been used in this project. So I'll move to the setup. The setup contains the UART initialization, the initialization of the synchronized primitives that have been used to maintain synchronization of the input parameters, the ECG buffer mutex, help state mutex, SOS stop semaphore, and I2C mutex. We've also created 3 software timers. That's for a low blood pressure monitoring timer, the MQTT reconnect timer to check if there's a loss of connection of MQTT, and fall reset timer, which is also a one-shot timer just like the blood pressure monitor timer. Xtask create pin to core is a function that has been used for pinning the various tasks to either core 0 or core 1, as you can see. So with the various tasks have been pinned to core 0 and core 1. Void loop is usually a loop, is the function that keeps on running again and again. So it's a standard Arduino loop and it's unused in the FreeRTOS implementation, but it has been used for keeping the MQTT connection alive in our case. So I'll first want to cover the various tasks. So I'll first head to ECG analog task. So the ECG analog task, as you can see, it runs at 125 hertz. The sampling has been set to 125 hertz, and I can head to the. So I'll be covering this. So I'll be covering the ECG functions later on, but for now, I'll just be explaining the task. So the task, it runs at 125 hertz. That's at an 8 millisecond interval. It reads the analog value from ECG pin, applies a high pass filter to remove the DC component, and then pushes the data into the circular ECG buffer using this function. And it takes the help of ECG buffer mutex, which we already defined in the synchronization primitives. so as to maintain a proper synchronization of data. Now I'll move to the oximeter I2C task. So the oximeter I2C task, it pulls the max 30105 sensor for heart rate data. It runs every 20 millisecond. It acquires the I2C mutex, as you can see, and reads the infrared values and computes blood pressure blood pressure monitoring value, and it gives the semaphore, as you can see. So semaphore has been used quite semaphore and mutexes have been used to maintain synchronization. We can get the beats per minute and then average out the samples so that we get a smoothed out blood pressure monitoring value before updating the global state. Besides this, heart animation has been triggered using this particular function, as you can see. Now I would want to move into the accelerometer task, which makes use of the HML classifier, which is running on Core 1, as I discussed before. So this task pulls the LIS 3DH accelerometer at 50 Hertz, and it buffers the rate data and runs the fall detection inference engine, which I'll be talking about later. If the fall is detected, it increments the fall counter, triggers an SOS. If the consecutive fall threshold that has been defined by us, consecutive fall threshold is met. So I'll be explaining the functions of the accelerometer later on. So for now, I'll move to the other important task that has been defined in the main. That's the MQTT send task. Mm, So this task has been named as send to Node-RED task, and it publishes the telemetry to the cloud. It runs every 1 second. So what it basically does, it formats a JSON payload which contains the blood pressure monitoring data, the fall status data, the SOS data, as you can see, and it publishes it to an MQTT topic. It handles automatic reconnection as well if the Wi-Fi connection drops. Now, the other important task that I would want to discuss, since we have want to discuss the important ones only over here in the main CPP, is the SOS task. So I'll move into the SOS task. So the SOS task, it manages the emergency alert outputs. So as you can see, semaphores has been used. So it gets blocked on a semaphore until triggered by a fall detection or by a button press. So when it is active, it drives the speaker in a specific SOS pattern, usually via AW9523 or using PWM. And it forces the display to display an alert message. The logic for which has been written over here. It's quite basic, this logic. So now I'll move to the IO expansion and control part. So this is the AW9523.cpp file that we found on the internet, but there were certain things that did not configure well and work well, which have been written by us from scratch. So this module, it interfaces the AW9523 GPIO expander, which is used to expand the limited pins on the ESP32S3 for button inputs and for LED speaker control. So the various functions of this, I'll be discussing those. So AW9523 is a constructor. The parameter that it has is a address, and the address is the I2C address of the expander, which by default is 0x58. Then there's the begin, which initializes the driver and points to the I2C bus instant. So it resets the chip, performs a soft reset, resets the chip or power cycle delay. It verifies the chip ID to ensure hardware presence and also configures default port directions, input for buttons and output for speaker and LEDs. It returns a true if the chip is detected, false otherwise. So the logic for setting the output registers to pull up, pull down, and for setting it as a button and then as an output has been written down by scratch. So this bare metal programming has been done by us. So as you can see, we have made use of all these functions to change the pin mode and to set GPI mode and to also make use of bit shifting for digital reading the registers and also writing to that particular registers. So this complete logic is written in this file. So the next important file that I would want to discuss is the ecg.cpp file. So the ecg.cpp file, this module, it handles the raw analog interfacing and the signal conditioning for the ECG sensor. The ECG init function, it configures the ADC, the sample rate and lead off detection pins, sets L0 plus and L0 minus pin as inputs to detect if the pads are disconnected, configures the ADC sampling resolution to 12-bit and the attenuation. As you can see, set resolution, set attenuation, read resolution, and this value has been set to 12-bit. So this is the ECG init that begin function. Now we'll move on to the ECG uh, uh, reading function. So this function, it reads the value, captures a single raw sample using the analog read function and checks lead off fins bus. If the lead offs are off, return the specific code or flat line. So I can move into it, but the declaration of this, since we're done with this, I'll be closing this. So this is the declaration of that particular file and header. So this is a haul function, as you can see, that's already been created and provided to us, and we have used it for sampling and setting the attenuation. Now this is the filter, the Butterworth filter that we have, digital filter, IIR filter that we have implemented. It's an order for filter, and the various mathematical calculations have been done are highlighted over here. This has been done for cleaning the signal for visualization and processing. So the infinite impulse response high pass filter, it removes the baseline and also a potential notch filter has been implemented to remove the AC signals, the 50-60 hertz power line signals that can cause interference in our small ECG signals, because the ECG signals are of lower power and voltage as compared to the AC signals of the power line. Besides this, the read logic of the ADC and how the band pass filter is applied is written in the update function. So this has been broken down into various classes and objects, and the functions are written in the ecg.h. As you can see, the classes have been defined over there, and these have been used in ecg.c++. Now I'll move to the AGI implementation. That's the star feature of this project. So how we have used Edge AI on the on this particular board, and that comes in the fall detection.cpp. So this file, it wraps the Edge Impulse SDK to provide high level inference capabilities. So I'll be talking about two or three more functions that are in the fall detection uh, .cpp file, fall detection.cpp file, and the fall detection init. So in the init or the begin function, we allocate memory for the neural network model, and we have called the run classifier. Uh, yeah. So this will give us a better overview. I talked about the accelerometer task in main.c++, and over there we had called the run inference model. So this run inference model, this is this has been defined in the fall detection.cpp file. So as you can see, run classifier has been used. It verifies that if the model fits in the RAM, the run classifier in it. And since I would want to go deeper into it, so I'll be closing the ec.c++ and I'll head into the declaration. So definition, I'm at. Yep. Uh, so as you can see, by hovering over it, you can see that the overloaded function run classifier defaults to a single impulse. So the run classifier, what it does is it converts, uh, it passes the result vector. As you can see, the signal, the vector. So the fault detection run inference is used for classification of the movement data. Uh, the run classifier function, it calls the run classifier function. It converts the raw accelerometer values. As my friend has discussed before in this project, before in the explanation of this project, he has explained the Edge AI, the entire layer. So for now, that's handled by the SDK, and the run classifier function handles this particular process. So it passes the result vector, the probability for idle, waking and fall, walking and fall are detected using it. Then using the index, the fall detection is fall detected index, which we can find over here. It's a helper function which helps us to interpret the result. This returns a true value if it matches and the confidence level is greater than 0.8. So most of the chunk is handled by the SDK layer of the Edge AI Impulse, and that has been covered by my friend. Um, so basically, we just have to focus on the run classifier function and how it works over the various raw features array has been explained over here, and then a basic comparison of the various labels uh, has been done. This has serial print has been done for debugging, and the predictions have been printed in the run inference model. So it's handled by the SDK layer. The most of the stuff is handled by the SDK layer. Now moving on to the next important part, that's the display management. So the display management, I'll want to move into the OLED.cpp. So the OLED.cpp, as you can see, is in the hex format. These have been assigned for the heart, the normal heart. These have been hard coded. The animations that you will see on the screen, and the logic has been written below. So it manages the visual feedback on the OLED screen, draws the various vital signs, the status icons, and the emergency alerts. So the init function, it starts the display driver, as you can see, over SPI. It works over SPI. It sets the text color, the text wrapping, and the various parameters. So the various update functions for drawing heart, for triggering the heartbeat have been defined. Then there's the main update status function, which is a routine UI update. It draws the top bar with an MQTT and Wi-Fi icons, and it clears the blood pressure monitoring area to prevent ghosting. Besides this, it prints the BPM value in large font. So all of this, drawing the heart, showing the BPM value, and drawing a dynamic heart icon has been done using the update status, which routinely calls the various functions that have been written in OLED.cpp. Besides this, there's also the graph that does real-time plotting of the ECG signal. So yeah. Um. So this is how the main oximeter dot the OLED.cpp works. I'll move to the oximeter.c++ file. So the oximeters.c++ file is the driver interface for Maxim Max 30105 or 30102 sensor. So it also has the three main functions: the init, update, and the get heart rate. So the init, that's the initialization of the various values, the configuration of the sensors, the sampling and the pulse width and the ADC range that have been set, and the sampling rate is usually 100 hertz or 400 hertz. We have set it as 200 hertz, and it initializes the particle sensing mode. Besides this, there's the main update function, which is basically an implementation of a state machine for beat detection. It reads the FIFO buffer from the sensor and passes the IR signal to the beat detection algorithm. That's this, the check for beat algorithm. As you can see, if a beat is detected, so the logic, since I can't be covering all of it in this explanation, I would want all the readers to go through the logic if they want. And it has been written in the check for beat logic. If a heartbeat is found, it calculates the time delta since the last bit to derive the instantaneous BPM. And as I already discussed before, the BPM values have been then averaged out. So it updates the moving average to filter out noise. And then it averages out the value, the BPM value, as we saw before. And so this is the oximeter update function. And so it's a state machine, as I told before. And then there's a get heart rate function that is a getter function for other modules. And the current gives the current smoothed BPM value. So the BPM value is returned. As you can see, averaged out. These were used before, and as I discussed them before. And now I'll move to the connectivity part and I'll want to discuss the Wi-Fi helper.c++. So this wraps the standard Arduino, Wi-Fi and MQTT libraries to provide robust connection handling. So the Wi-Fi connect, it makes use of the Wi-Fi helper function, again the initialize functions and checking if it's connected and get the RSSI values, and this print is just for printing the data. So the printing the data for debugging. So it makes use of Wi-Fi connect and MQTT reconnect. MQTT reconnect ensures that the cloud link is active. It checks if the client is connected. If false, it generates a random client ID to avoid broker conflicts and attempts reconnection. So it resubscribes to the control topics, that is the SOS trigger upon success. So now other helper utilities that have been used. .c++. So the UART.c++ has been used. So we have made use of UART locking for thread safe locking. So it has used a mutex to, so this has been, I'll want to move to the header files for better description. These are the various functions that are present in the UART file. So then UART.c++ has been used for all the logging related tasks. It formats the string, the printf style, and sends it to serial. Then there are other various dependencies. So oximeter, I2C task, and ECG analog task. They collect raw data on core 0, as I discussed before in the software architecture. And there's also a shared buffer, which I have talked about before, the ECG buffer mutex. So I'll go to its definition where all it has been used. So it has been defined in the setup. So the data that's written into the global variables is buffer protected by I2C mutex and ECG buffer mutex. And then the accelerometer task runs on core 1. As described here, it reads motion data and runs inference. And health monitor task, it checks if BPM is below threshold or fall counter is greater than 5. If threshold is crossed, the SOS state flag. SOS semaphore, it is to stop SOS. And as you can see, I'll go into the SOS task. So this is used for checking if the SOS is playing or not. So it sees the flag and activates the speaker or the LED OLED in the OLED screen. And the MQTT send task, as I discussed below, send to node read task. It sends the flag and sends an emergency state adjacent packet to the backend. So this in overall is an overview of how this program works. And my friend Karthik has explained the Edge ML inference, the Edge ML classifier inference layer. And now that's all from the software part. I'll recommend all of you to go through the README files if you want to learn more about it in detail, and also go through the various files we have created. A special emphasis on the AW 9523 because the bare metal logic has been developed from scratch by us. So that's all.